So we know that in the 1980s and in the 1990s, X-ray lithography was targeted for the application of IC manufacturing. But now we know that X-ray lithography will not be used for the high resolution manufacturing. Actually, I think it will be more used for the high aspect ratio manufacturing. So we can make a high aspect ratio structures using X-ray lithography because of the very high penetration depth by the X-ray. So this technique is called a Liga process. So Liga, it means lithography, electroplating, and molding. And now we will look at the Liga process. So first, we do the X-ray lithography. So this is the X-ray mask with absorber on top of the membrane. So we have the resist. The resist can be a PLMA, typically a few hundred micrometer. After lithography and development, so we get the structure in the resist. Then we do an electroplating process. Typically, the metal is nickel. Then we remove the resist, so we have the nickel mold. Then we can use the nickel mold to make many copies of the polymers. This is by hot embossing or injection molding. So we know that hot embossing and injection molding are very high throughput, cheap process. So this way we can make a high aspect ratio polymer structures. So why Liga is good? So because first we can make a very high aspect ratio. So this is because of the high penetration depth of the X-ray. And you can see here, in this example, so the height is 400 micrometer, so the width of a few micrometer. So this one is done at deep X-ray lithography, a few angstrom wavelengths. If we go to even smaller wavelengths, we have even higher penetration. So here you can see we can get 3 millimeter thick structures with the side wall, the slope only a few micrometer. So normally we can get a side wall slope less than 1 micrometer per millimeter. So the surface is also very smooth. So the surface roughness is better than just a few tens of nanometer. But we know that even with those properties, so X-ray lithography is not widely used. So there are two reasons. So first, so in the late 1980s, so we have another resist coming out. That is the SU8, this resist. So we can use normal optical lithography and this resist to give similar high aspect ratio structures. So this is done by the normal photolithography at 405 nanometer wavelengths. 405 nanometer. This is the H line for the mercury arc lamp. So we know that for the I line is 365 nanometer. So this is for the I line. For the case of SU8, the absorption of this wavelength is larger than the absorption at this wavelength. So that's why for this paper, this wavelength is filtered out. So only use this relatively long wavelength to have even higher penetration into the SU8 resist. So first, SU8 gives you the low absorption. Secondly, so because it is chemically amplified resist, so it is very sensitive. That's why we do not need. So the exposure time is still acceptable. Another competing technology to the Liga process is the deep silicon etching. So nowadays, deep silicon etching can etch really fast, can go to a few tens of micrometers per minute. So it is easy to etch through a wafer, a silicon wafer. So a third reason is that for the Liga process, so we need a synchrotron radiation, which we know is not very widely available. There is only one, the Canadian red source in Canada. Here are examples of the Liga, the structure made by Liga process. This one is called a PLMA. This is the nickel structure by electroplating into the PLMA, and those are the details. So this can be used for the acceleration sensor. So accelerator sensor is used in the crash for when there is a collision. So we need a accelerator sensor to trigger the airbag. So this is also used in the cell phone. When you flip the cell phone, the screen will be also flipped. So this is done by the accelerator sensor. But actually today, accelerator sensor is only made by the silicon, not by these structures, because silicon we know is easier to fabricate by the deep silicon etching process. So how does this acceleration sensor works? So here we have the block of the mass. So one of them, for example, this block is movable. It's floating. So we have, when the car suddenly gets stopped, so the mass, for example, this mass will move because of the inertial force, the mass will move this way. This one fixed. Maybe this one fixed. This one will move. So when it moves to here, then the gap will be different. So difference of the gap will change the capacitance between the two structures. This way, the acceleration can be detected. So we can play some tricks for the accurate lithography. For instance, here we can tilt the wafer. We can tilt the wafer to make structures like this or structures like this. So this is here the example is for the accurate lithography. So people do the similar things using the UV lithography and SU8 resist. So you can see make something like this. So this can be used as a filter. If the liquid flows this way, then it will be some particles will be filtered out. So here I want to ask you, can we use positive resist to get similar structures? So the answer is no. So if we have something like this, it has to be done by using the negative resist, because negative resist will be cross-linked. So when you expose this way, this part will be cross-linked. When you expose this way, this part will be cross-linked. But for the positive resist, you cannot make structures like this. So here is another example of the fabrication tricks. So here we use two layers. So one layer is SU8. So SU8 is a sensitive resist. Then we have the PMA layer. So first, we pattern the SU8 layer. Because SU8 is chemically amplified resist, it is very sensitive. So the dose to expose the SU8 is not high enough to expose the underneath PMA layer. So the PMA will not be affected because of the low dose. Then we expose the PMA layer. So the dose to expose PMA is pretty high, but this layer here is already cross-linked. So the high dose will not affect the cross-linked SU8 layer. After development, we can get two-level structures like this. So here the feature size is around a millimeter scale. So now let's look at accurate optics. So we know that for the accurate, the wavelength, so the reflection index is almost equal to 1.0. So normally for the visible light, if we have the inner phase, the light coming in, there may be diffraction and reflection. But for the X-ray, this will not happen because n is almost equal to 1. So there will be no reflection. There is also no reflection. But if this one is a bulk material, if this is bulk, for example, if this is silicon, if this is single crystal silicon, we know is a single crystal material, there will be accurate diffraction. Then the accurate will come out. But this way, effectively, the accurate can come out and looks like accurate is diffracted. But normally, just at the inner phase, accurate will not be diffracted. So to focus the accurate, we cannot use the normal lens. So normal lens is something like this. So this kind of lens will not work. What we can do, we can use the zoom plate. We can use zoom plate for the X-ray optics. Here is the idea of the zoom plate. So we have the X-ray coming in. And this area is blocked. This area let it pass. This area blocked, then it pass, block, and pass. So effectively, if this part corresponds to this part, so it is this phase, then we have this black color is opposite phase, because this, then we have this area, the positive phase again. So you can see here is, from here to here is distance is d, from here to here is d plus lambda, then d plus 2 lambda, d plus 3 lambda. So effectively, those areas here, this opening, so like 1, 3, 5, they will interfere constructively. So if we block the 2, 4, 6, that means if we block those area, then all the light will come out, interfere constructively. This way we get effectively actually get focused. So we have a focal point here. But it is different from the normal lens, because there can be more than one focal point. For example, if we look at this point, from here is D prime, so we say like D prime. Then from here to here is D prime plus, from here to here is D prime plus 2 lambda. From here to here is D prime plus 4 lambda. So from here to here, D prime plus 8 lambda. Then all the light will also interfere constructively at this spot. But that means there will be a secondary focal point. then there will be many other focal points. So you can see it's different from the normal lens like this. For this lens, there will be only one focal point, but for the zoom plate, there can be quite many focal points. So you may ask, so how come the acrylic they only come to here? So when the acrylic, for example, if we look at here, it can come to here as we want, and it will also come to here, and it will also come here. It can go to other directions. The same thing for other here. So how come only this point it got focused? If you do the calculation, even though there may be actually coming to here, but if you add them all together, so most likely they will be cancelled out. So the light intensity here will be weak. Only the light at the focal point they are strong. Other places they have weak light intensity. This is another difference from the normal lenses. Here is the zoom plate, circular zoom plate. This one actually comes in and it will be focused. For the fabrication of the zoom plate, normally it's fabricated by the electron beam lithography followed by electroplating. This is the gold structure by electroplating. So now let's look at how to design the zoom plate. So here we have many circular structures. So we want to know what is the radius. So what's the radius for the red color, blue color, red color, blue color? We need to know the radius so that we can design the zoom plate. So the requirement is that, so first, the center part we want to block the light. This part is blocked. Then we have this R1, this R1. So R1 is given by F plus lambda over 2. R2, the radius for R2 is F plus lambda. So R3, this part again, lambda plus 3 lambda over 2, then lambda plus F plus 2 lambda. So the area between R1 and R2 is transparent. That between R2 and R3 is blocked, and so on. So this way we get a constructive interference to get the light focused. So the requirement is like this is the requirement. This is the requirement. So now we want to know what is R1, R2, R3, and R4. So first we use for this is the rectangular. This is the right angle triangular. So we have F square plus Rn square. So Rn square equal to F plus n lambda over 2 square. So then we have this formula here. Because of the small wavelengths, we can ignore this term. So we have this one. So Rn equals to n lambda f. Rn equals to n lambda f. So this is how we design the zoom plate. So we know the wavelengths we want, we know the focal point we want, we know the number, then we know the Rn value. So you can see that even though this is a lens, this is not a good lens because the different wavelengths will be focused at different spots. So this is not good. They have very large dispersion. For the normal lens like this, even though there is dispersion, the dispersion means the index, the refractive index depends on the wavelengths, but the dependence of n on the wavelength is very small. As a result, the different color of the light will be focused at nearly the same spot. That's good. But for the zoom plate, as you see, the different wavelengths will be focused at very different f. That's why the zoom plate is not good lens. It can be used to form the image, but the image is not very nice. So now we want to see how small spot we can be focused. We want to know the resolution of this zoom plate. So because we have an aperture here, so we want to know the sin theta value. So when we know the sin theta value, we know the numerical aperture equal to sin theta. Then, according to the Rayleigh criteria, the resolution is given by 0.61 lambda over NA. So we want to know the sin theta value. So first, we know if we try to calculate the zone width of delta R value, this delta R. So here you can see the same thing. This is delta Rn. That is the width of the outermost zone. So delta Rn equal to Rn minus Rn minus 1. So because of this formula here, so it's given by and equal to this term Rf lambda f over Rn plus Rn minus 1. For the n, when the n is large, so Rn and these two numbers they are roughly the same, so equal to 2 times Rn. The 2 times radius is the same as the diameter. So we have this formula here. Then we have d delta lambda. So d delta lambda equal to lambda f. D delta lambda equal to lambda f. So f equal to d delta lambda over d delta r over lambda. So the numerical aperture here, the sin theta, for the small theta, the sin theta is roughly equal to tangent theta. The tangent theta equal to Rn divided by Rf divided by f. So Rn divided by f. So equal to radius divided by f equal to diameter divided by 2f. D over 2f, f is here, so f is here. The d is cancelled out, so we have lambda over 2 delta r. Then resolution given by this formula, 1.22 delta lambda. So the conclusion is clear. So the resolution is given is the same order as the width over the outermost zoom. So this is make the fabrication of the zoom plate very difficult. If we want, say, 10 nanometer resolution, then the width will be about 10 nanometer. If we want the thick enough gold to block the X-ray, it will be challenged to fabricate tall gold structures with only width about 10 nanometer. So now we see that X-ray can be focused by using the zoom plate. But this is not still imaging. So to form the imaging, we want to know that if we put the object here, and it will form the image on the other side. So following the example here, so here we have the distance is f plus n lambda over 2, n lambda, this term n lambda over 2. So the requirement for this to form the image here is the same. We want Qn from here, Qn plus Pn equal to Q plus P plus n lambda over 2. This is the same requirement, similar requirement. We want them to be n lambda over 2 for the design of this zoom plate. So we know Qn equal to Q squared plus Rn squared. They have the square root. So we want to know what is the case for this one. We want to do some approximation. So we take the Q out. So this one equal to, if we take the Q out, this one equal to Q1 plus Rn squared over Q squared. So how to do this approximation? If the radius is much smaller than Q, if the radius is much smaller, if this term is much smaller, this one so equal to Q times 1 plus 1 over 2 Rn squared over Q squared. Equal to Q equal to Q 1 plus 1 over 2 Rn squared divided by Q squared. So where we come this factor of 2? So this is because we have learned about approximation. So 1 plus x power n equal to 1 plus nx. So we have seen this very useful approximation. So this will be valid if x is very small, and nx is also very small. So in this case, we have square root. So n equal to half 1 over 2. That's why we have this one. So now we get so Qn equal to this one, and Pn we do the same. So Pn equal to this one. Then we put them into this equation. We get this formula. Then we get this formula. We divide this one 1 over f. So f equal to Rn squared divided by n lambda. From here you can see that Rn equal to n lambda f square root. So this is the same as here, the same as this one. So this formula here, this is the length equation. So we know that for the regular optical length, so we have the equation 1 over q plus 1 over p equal to 1 over f. So I think you learned this. You must have seen this equation in maybe your high school physics. So now we see that it is actually, if we have objects here, and it will form image here. But this is not enough. To form the image, you need a third improvement. So you need to assert a proof. So you want to know that the height here, so from the light from here, come to here. So that means so the light actually come from the point, top point here, come here and up to this point. So this is equal to this one. Equal to from here to here. plus n lambda over 2. Actually, if you do some math, this can also be proven. That means the arrow, the top of the arrow will form image here. So this one here we have the example for the case of X-ray. So the same idea, the zoom plate will also work for the visible light and for all the light. For the visible light, it is called Fresnel lens. This is called a Fresnel lens. It is useful. It's very easy to make it. It's very cheap to make it for the visible light. But as we said, this is not good lens because of the dispersion. The different wavelengths will be focused at different spots. So now we want to see Fresnel lens for the visible light. So if you do a Google search, of the Fresnel lens, you can find many of it. So this piece of plastic is a Fresnel lens. This one has 3 times magnifying power. It is a sheet. This is the sheet. It's only 0.5 millimeter thick. So that means the main advantage for the Fresnel lens compared to the regular lens is that it's very thin. It's only 0.5 millimeter. So in theory, the thickness can be comparable to the wavelength. But in reality, if this is only 1 micrometer, it is hard to form a stable structure. So it only cost $18. So how to make a lens, a Fresnel lens, only $18? This plastic sheet can be made by hot embossing or injection molding. So when you do the molding process, we know the molding process is very low cost and high throughput process. But this way, we can make very cheap and very lightweight lenses, and very lightweight and also very thin lenses. So now let's look at how to fabricate the zoom plate. So the fabrication process is straightforward. So first, we have the membrane, the silicon nitride membrane. So we coat a thin layer, conducting layer of gold. Then we coat PLMA as the electron beam with this. So we do electron beam lithography development. Then we do electroplating of the gold. So finally, we can remove the PLMA to have the gold structure. So here is an example of the zoom plate. For this one, the outermost zone is 30 nanometer outer zoom width, giving you the resolution about 30 nanometer. But this is because of this one. So the resolution is the same order of the zoom width of the outermost zone. So here in this case, it's 30 nanometer. So how to make the membrane, silicon nitride membrane? This one we have seen it. How to make the silicon nitride membrane? So we have seen this before. So this is the process to make the silicon nitride membrane. So we do the silicon nitride membrane by the white chemical etching using QH. So this is very useful method to make very thin membranes. So here is the setup for the imaging using X-ray. So here you can see, so we have the synchrotron radiation. We come from this ARS, is advanced light source in Berkeley in California. So we have this mirror. So this mirror can be a bulk of the single crystal silicon. So this X-ray is not bended by the refraction. It is bended because of the X-ray diffraction through the single crystal silicon. So we have one zoom plate as a condenser lens. We have the pinhole. We have the sample. So this sample can be scanned along the X and the Y direction to have the signal from every point. Then we have another lens that forms the image. So the resolution in this case is 15 nanometer resolution. So this is published in 15 years ago in Nature. You may ask, well, how come a resolution of 15 nanometer can give you a Nature publication? So we know that the 15 nanometer resolution is very easy to achieve by using the scanning electron microscope. So when we do the SEM, 15 nanometer, we can even get just a few nanometer resolution. If we go to the transmission electron microscope, you can get even better resolution. So what is the use of this? So why it is published in Nature? So this is because this process is still an optical process. So the resolution is much higher than the resolution of the optical microscope. For optical process, we do not need a high vacuum. So we can do this process in a liquid. So we can do the imaging of the biomaterials in the liquid, not in the vacuum situation. This is the main application for the X-ray imaging using a zoom plate as the lens. So here's the idea for the bioimaging. So we have for a typical cell, so we have the water. There will be water. There is also the protein. This is the protein in the cell. Here is the absorption loss for the water and the protein. You can see if the active energy is here, if we have active energy at this spot here, then the water penetration go to about 10 micrometer. So typical cell is less than 10 micrometer. So the water, it will be transparent. The water will be transparent, but the protein will block the X-ray. So as a result, so we get the contrast of the cell in the water environment if the water is less than on the order of 10 micrometer. Now here's the attenuation loss. So how to get those kind of peaks is different from what we have seen before. So if we look at before, so we have a peak. So this is accurate absorption. This is accurate absorption for the casing of the PMA. But this one is the absorption coefficient. The drawing here, this is the absorption coefficient alpha. For the absorption coefficient, the higher energy, lower absorption. So here you can see we have for the PMA we have two peaks. So one peak is near this is 100 electron volts, 200, 300. This one is near 300. One peak is near 300. Another peak is this is 500 is more than so between 5 and 600. So now we come back. So one is 300, the other one is between 5 and 600. So here we can see for the 300, this corresponds to the absorption of carbon. For the 600, 500 and 600, this corresponds to the absorption of oxygen. So we know that for the previous slide, so we have the material PMA. So in the PMA, so we have carbon and we have oxygen, but there is no nitrogen. So in the previous slide, what we draw is the absorption coefficient. So we see a trend, something like this. Higher energy, lower alpha. But here we show the penetration loss. The penetration loss is given by 1 over alpha. That's why we see a trend like this, because this is 1 over alpha. The previous drawing for the PMA is alpha. So again, so the energy here will be given by oxygen, will be given by something like 13.6 Z minus sigma squared divided by N squared. For the peak here, oxygen, nitrogen, carbon, N equal to 1. That means this is the absorption for the K shell electrons. Z equal to atomic number. For the case of oxygen, Z equal to 8, nitrogen 7, carbon 6. Sigma is the absorption, is the screening factor, which is about 1 or 2. So we cannot see, so for water we have oxygen and we have also hydrogen. For hydrogen we know if Z equals to 1, this is the hydrogen, there will be no screening effect. So hydrogen energy is 13.6 electron volts. It is should be, hydrogen should be here, 13.6 electron volts. But how come the sulfur is here? So normally you can see higher atomic number give you higher energy. So the sulfur is atomic number is 16. How come this one is, the energy is lower? So this is because for the case of carbon, nitrogen, oxygen, N equal to 1, so K shell. For this sulfur energy here, the N I think should be equal to 3. 3 means KLM, so this is M shell absorption. So here are the examples of the X-ray imaging. This is the malaria-infected red blood cell. You can see X-ray imaging. This is optical microscope image. So you get better resolution than the optical microscope image. Now here again, this is the imaging of this. It's called a cryptopyridium using the wavelength near 2.4 nanometer wavelength. You can see the clear image. So 2.4. If you look at here, so the edge is 2.3 nanometer. So 2.4 is right below the absorption by the water. So now we come back to the zoom plate. There is a Canadian company whose main product is the zoom plate. This company called Applied Nano Tools. So this company have, I think, have 5 to 10 people. Their main product is the zoom, accurate zoom plate. So this is the zoom plate. So they do this by electron beam lithography. So this is the image of the SEM image of the zoom plate. So here is the metal here is gold. So gold absorber on top of a very thin membrane. So the gold line, they are not connected. You can see it's broken. There are lots of broken parts. So this is because this work is done by electroplating. So before we do electroplating, we need to make the E-beam resist structures. So the black color here should have been electron beam resist like a PLMA. But if we have very thin and tall PLMA polymer structure, it will not be mechanically stable. So we need some those black dots, those parts, to make sure that the line they will not fall together, because this black will support the white lines. So this part will support the white resist lines. So this is the different zoom plate. So this one, the zoom width is 15 nanometer. That means the resolution for this zoom plate is 15 nanometer times 1.22. The thickness is 0.0 micrometer. This one aspect ratio is 17 nanometer over 15 is 1 to 4, nearly about 1 to 5. This thickness of the gold absorber, outside diameter is 100 micrometer. The number of zones is a few thousand. The focal length is a few hundred micrometer. So they have many different types of the zoom plate. So each of the zoom plate, the cost will be about $10,000. Okay, thank you.